Today we start our second chapter of the algorithmic course. We will see in this chapter two approaches, which are the divide and conquer approach, as well as the dynamic programming approach. Let me now see another problem, which is a typical problem based on the dynamic programming approach. In this problem, we will imagine that a robber robbing a safe is found with objects of varying sizes and values, but has only a small knapsack of capacity W. The problem is to find the combination of objects to be placed inside the knapsack in order to make the maximum gain. So we will help the robber to get the maximum gain after robbing his safe box, let's say. So let me now try to model our problem. Let a knapsack with maximum capacity or weight, which is W, and a set of n objects, a set T of n objects, T equal O1, O2, On. Each object OI has a weight which is small wi, which is a positive integer, and has a benefit which is equal to bi. The problem consists in finding a subset of objects as belonging to T as included in T, so that the total benefit is maximized without exceeding for sure the capacity W of the knapsack. So our goal is that we will take the maximum of the sum of I belonging to S of Bi such that the sum of I belonging to S of Wi is less than or equal big W, the capacity of the knapsack. Now, using a naive algorithm that searches the maximum benefit for a total weight less than W by testing all the possible combination of the n existing objects, so this algorithm will have a time complexity which is big O of 2 power of n. Knowing that there are 2 power of n which are 2 power of n real object or 0, so the total will be 2 power of n. The total of the possible combination of n objects. Let me make the test with 2 objects to understand it well, to simplify things. Suppose I have only 2 objects, O1 and O2. Okay? What I can put inside the knapsack? I can put nothing, 0 object. This is the first choice. If the weight of O1 is greater than the capacity and the weight of O2 is greater than the capacity. Second choice, O1 alone. Third, O2 alone. Fourth, O1 and O2 together can fit inside the knapsack. So for 2 objects, I have 2 power of 2. That's all. If you take 3 objects and you take the possible combination, for sure we'll get 8 possible combination by using the same approach. Okay, now Using dynamic programming, the problem can be formulated as follows. We denote by VKW the maximum benefit of a knapsack of capacity W achievable with objects 1, 2, 3, etc. up to K. So VKW, the maximum benefit, is equal to VK minus 1 comma W if WK is greater than W. Otherwise, it's equal to maximum Vk minus 1 W, comma Vk minus 1, comma W minus Wk plus Bk. So here, best solution after adding K minus 1, and here replace an item or items with the case item. So what we are doing here, first of all, if the weight of the object at a certain moment that has to be added is greater than the current weight of the knapsack, because we'll take different weights of the knapsack, starting from the smallest weight, which is 0, going up to the real weight of the knapsack by incrementing the number. So if the weight of the current object is greater than the weight of the knapsack, we will take the previous value. That means we will not, as if we don't add the object to the knapsack. By contrast, if the weight of the knapsack can contain the object at a certain moment, so we will calculate the new value of VKW by taking it as the maximum of Vk minus 1W, which is the previous value, and the new value, which is Vk minus 1, comma W minus Wk plus benefit of the object K. Why here W minus Wk? Because we will take the value as if other objects does not exist, in order to let enough space to the new object to be added inside the knapsack. So here what we will do, as we mentioned for the dynamic programming approach, we will use some table in order to store the solution of sub-problems to avoid repeating solved solution. So here for the knapsack problem, we need a matrix, in fact, so a table of 2 dimensions. So, or an array of 2 dimensions will be created, whose rows will be indexed by the number of objects going from 0 to n. We will number the objects starting from 0 up to n, and the columns will be indexed by the weights of the knapsack. We will take different weights incrementally, starting from 0 up to big W, which is the capacity of the knapsack. The algorithm to solve the knapsack problem, we will see a pseudocode for solving it. So for W equals 0 to W, for we start the initialization, V 0W equals 0. So we will initialize the first row to the value of zeros. Now, for I equal 1 to n, vi of 0 equal 0. We'll also initialize the first column to 0. Pay attention, this is the basic and trivial solution of these subproblems. Because of what? Because for the first row, we have 0 object, so nothing can fit inside the knapsack. We cannot put anything inside the knapsack, and thus the values of benefits will be 0. Same thing for the first column. The weight of the knapsack is 0, so we cannot put anything, any object inside, and thus the values for this column will be 0. Now we will start to fill our matrix for I equal 1 to n, for w equal 1 to w. 1 to n will go line per line, and here w equal 1 to w to go through the columns of a specific line. We'll do the following test. If wi, here we are applying our previous proposed formula to model this knapsack problem. So if wi is less than or equal w, what we will do, that means the weight of the object is less than the current weight of the knapsack. So we will take the maximum by this way. If bi plus vi minus 1, comma, w minus wi greater than vi minus 1, comma, w, which means just the previous value, what we will do, we will assign to viw bi plus vi minus 1 w minus wi. Else we will take the previous value viw will be assigned to vi minus 1, comma, w. Else, that means what? The object cannot fit, so we will keep the previous value vi w equal vi minus 1 w. The complexity of this algorithm is big O of w multiplied by n, which is a pseudo-polynomial complexity. Why pseudo-polynomial complexity? For example, if w is equal to n, it will be n power of 2. If it's equal to n power of 2, it will be n power of 3. If it's less than n, so it will be less than n power of 2, and so on. But for sure, this complexity is much better than the exponential complexity discussed earlier if we use a blind approach in order to solve this problem. Let me take an example to understand more this knapsack problem. Giving a knapsack of capacity 5, so big W equal 5, with the following objects, object 1, 2, 3, and 4. These objects having the following weights and benefits. Object 1 has 2 as weight, 3 as benefit. Object 2, 3 as weight, 4 and as benefit. Object 3, 4 and 5. Object 4, 5 and 6 as benefit. We will use this matrix, okay? So we need a matrix. The weight or the capacity of the knapsack is 5, so we need to start from 0 up to 5 for the columns. And we have 4 objects. We'll start by numbering the object. First object is 0. 0 is for 0 object, for nothing. And for the rest of the object, we'll use the number 1, 2, 3, and 4. If you have objects named, for example, A, B, C, D, we use as index 1 for A, 2 for B, 3 for C, and 4 for D, like here. And we keep it 0 for the case of 0 object. Let me apply our algorithm. We will start the first step of our algorithm. For W equals 0 to W, V 0, W equals 0. So what we will do here, we'll initialize the first row to the value of 0. Because of what? Because for sure, if we have 0 object, so the benefit will be 0 for any capacity. Second step, for I equal 1 to n, Vi of 0 equals 0. Same thing here. For a knapsack of capacity 0, for sure we can't put anything inside, and thus the value of the first column will be 0 for all the rows. Now we will go to the rest of our algorithm to calculate the value of the remaining cells of our matrix. Let me start. So from here, if we start our loop, we'll start from here with n now equal 1. N equal 1, we will go through the values of W from 1 up to 5. So for n equal 1, we have the first object for sure, which has 2 as weight and 3 as a benefit. Okay, if we try this object, it cannot fit here, so we'll take the previous value because its weight is 2. So we will take the previous value and we'll put it here. Previous value, which is at the previous line. By applying this test, okay, if Wi is less than W, the first line here, it's not the case, so we will assign to VIW the value of VI minus 1W, which is this value 0. We'll put it here. Okay, now for W equal 2. In fact, the weight is 2, so it can fit inside the knapsack. The object can fit inside the knapsack. And thus, what we will do, we will make this test. If Bi plus, first of all, Wi is less than or equal W, it's our case, so we'll continue the second test if you want. If Bi benefit is 3 plus Vi minus 1W minus Wi, okay, what's the value of W minus Wi? It's 0, so Y minus 1, so this cell. We'll compare the value of this cell, we will add to it the benefit, which is 3, and we will see if it's greater than the previous value, which is this one, which was 0. So for sure, 3 plus 0 is greater than 0, and thus we will put 3 inside this cell, which is the benefit plus the value of this cell. So this is what we will do. In fact, 3 will be put here. If we continue for the rest of the values, in fact, for sure we'll have the benefit 3 for all of them, because here we have only one object, and we have a benefit which is greater than for all the capacities, remaining capacities of the knapsack. So second one will be also 3, because 0 here, W minus Wi, 3 minus 2 equal 1, 0 plus 3 is greater than 0, so we put 3. And so on. 12 minus 2 is 2, the value is 0 in the previous line, greater than this 0 in the previous line of the same cell, so we put 3, and also for the value of 5 we will put 3. Now I will increment I to be equal to 2 to start with this row. So we'll work with the second object, for which we have a benefit which is equal to 4, and the weight of the object is equal to 3. Okay, the weight of the object is equal to 3, so if we come here for W equal 1, nothing will change. We will take the previous value because the weight 3 is greater than 1. Same thing for the second, W equal 2 is less than Wi, which is equal to 3, the weight of the object. So what we will do, we will take the previous value existing in the same column at the previous row. So we will take 3 and we will put it down here. Now, value of W is equal to 3, and the weight of the object of the current object, object 2, is equal to 3, so it can fit here. What we will do, we will apply this formula. We will subtract the size or the weight of the object, which is 3, from the current weight of the knapsack here, as we are doing what? As we are removing other objects to see if the benefit with this object is better. For this reason, we make this subtraction by going back to the column which is W minus Wi. So W minus Wi, we have the value 0 here, at position 0, 3 minus 3, it's 0, plus the benefit of the current object, which is 4, is greater than the previous value, which is 3, so we will put the value 4 here. So 0 plus 4 greater than 3, we will have 4 in this set. Same thing for W equal 4 now. 4 minus 3 equal to 1. 0 plus 4 is greater than, so we will put also 4 here. What for W equal 5? 5 minus 3 is equal to 2. What do we have in 2? We have a benefit which is equal to 3. We will add to it the value of 4. So 3 plus 4 is 7, greater than 3, and thus the value here will become equal to 7. Because of what, if you can imagine things, here at this capacity, which is equal to 5, we can have the two objects which can fit, object 1 and object 2. And their total benefit up to here is equal to 7. Let me continue in the same way for the third object now by incrementing I to be equal to 3. Okay, the weight of this object is equal to 4, so nothing will change up to 4. So for 1 we'll have the same previous value, for 2 the same previous, for 3 the same previous value. Now for 4 the object can fit here. For minus 4 we go in the column, will reach this column which is containing 0, plus the benefit of this object which is 5. In fact is greater than 4, so we'll put 5 here. For 5 now, 5 minus 4 is equal to 1, which contains 0, same thing, 0 plus 5, but 0 plus 5 is less than 7, 5 is less than 7, so we will keep 7, which is the maximum, instead of 5 here. Now for the last object, I equal 4, object number 4, we have the benefit which is equal to 6 and the weight which is equal to 5. As the weight is equal to 5, so nothing will change up to here. Up to here we'll have the same previous value. So we'll take 0, we'll take 3, we'll take 4, and we'll take 5. For W equal 5, the object can fit. 5 minus 5 is 0. The minute of the object is 6. 6 is less than 7, so we will take the value 7 of the previous row instead of 6. And here we have finally this maximum benefit, which will appear in the last cell of our matrix. This is the maximum benefit that we can get. In fact, it will appear here. Okay, up to here with the used algorithm, we were able to calculate the maximum benefit which will be appearing at the last cell in the previous matrix, the cell VNW. But now how to find the objects that will lead to this maximum benefit in order to put them inside the knapsack. So to know the objects that have reached this maximum value, an addition to this algorithm is necessary. But all the information that we need is existing inside our matrix. We will try to do some backtracking inside this matrix in order to identify these objects. So BNW is the maximum value of the objects that can be placed in the knapsack. Now we'll use this algorithm to find the concerned objects in order to place them and get this maximum. So we'll see this algorithm as pseudocode: set I equal n and k equal w. While I greater than 0 and k greater than 0, if Vik different than Vi minus 1k, then so we'll compare starting from the last element inside the matrix, the element that exists at position BNW. We'll compare the element with the element at the same column but in the previous row. So if the element is different from the element of the upper row, mark this element or object to be included in the knapsack. After that, we will decrement I equal I minus 1, and we will retrieve from K the weight of the object I. So K will be equal K minus Wi. Else, if the values are the same between the element at the cell and the element at the upper row, for sure of the same column, so we will simply decrement I to go to an upper row. Let me apply our algorithm over the previous example in order to identify the objects to be included. So here we have the matrix with the calculated values, and we know that the maximum benefit is this one. The 7 is existing here at VNW. So let me start. We will start the initialization. I equal N, K equal W. So we start from here, from this cell. We will compare the cell with the previous cell existing at the upper line, with the cell existing at the upper line. So the value is the same. So what we will do, we will go to an upper line. We will decrement I here, and thus we will go to an upper line. Simply that. Now again, we are at this line. We compare it with the previous one. The value is the same. We will decrement I and going to an upper line. Now we are here. Make the comparison. 7 is different from 3, so we will mark object 2 as an object to be included inside the knapsack because the upper value is different. After that, we will decrement I, and we will retrieve the weight of the object, which is 3, from K, which is for the moment equal to 5. So K will be equal to 2. So this object is marked, and we will come to here, to column 2. Now comparing 3 with 0, values are different, so we will mark this object, object 1, and we will retrieve the weight 2 from K, so we will reach the first cell here, and the work is done. Also, I is decremented, so the work is done, and these are the objects to be included inside the knapsack. We have the objects which are 1 and 2. Those objects have to be included. Okay, repeated rapidly. This is what we did. We compare with the upper. Once the value is changed, we subtract the weight of the object from K, and all the time we decrement I after any comparison.